Thank you so much. Excited to be here with you all and share some ideas about how chemistry is changing. No, okay. Let me just click. Boom, okay. So I used to teach a class called Deep Learning for Molecules and Materials. Really cool class. I wrote a textbook on it. And so I'm going to teach you all why you don't need to learn it, okay? So in chemistry, we have this idea of inductive biases. And this is basically things we know about the system we're trying to study. So usually we're doing machine learning here. So we have some molecules as input, some properties as output. And we have some ideas about how our output should respond to how we change the input. Sometimes this is like the physics of the problem. Like if we rotate the input, the output should rotate. These are things called equivariances. And they're related to basically the way we think about what a molecular structure is. So we can think about molecules being a graph. You can think about them as a point cloud. And when you write them down in that way, you're basically assuming some inductive biases. And these are called equivariances. And these equivariances have to do with what can be exchanged in your input or what can be varied in your input and how that affects your output. I'm not going to talk too much about them today because I'm just going to give you a flavor for them. And these are kind of obvious things like if you swap around the atom going in, then the output labels that are per atom should also swap around. If you rotate your input protein structure, the predicted output ligand should also rotate. But this is kind of what's driven a lot of the work, is that chemistry is a very poor field. It's very like a data scarce field. And so because of that, we kind of relied on equivariances a lot to reason about how to reduce the amount of data required. And so this is the kind of the classical approach to the graph neural network. If you go to a company that's doing deep learning for drug discovery and you ask them what is their machine learning approach, it's always the graph neural network. I have an animation of a graph neural network, how it works. I worked really hard on this. So let's just take a moment. That's really cool, huh? All right, I'm not going to talk about it, okay? And the reason why is that graph neural networks are very useful, but they suffer from a few problems, okay? One of them is what's called the Weisfeiler-Lehmann test. And that is that if you look at these two molecules, these are actually different molecules. They have different properties, different synthesis. But if you look at the actual graph that you get out of it, and you look at the neighborhoods, right? So like if you look at this red dot here, and it's connected to one red dot and two green dots, then you go over here, the red dot here is connected to one red dot and two green dots. In fact, most graph neural networks cannot distinguish between these two chemical structures. Each node in it has the same neighborhood, right? It's a very unusual kind of problem. And there's a few molecules like this. Anyway, you can solve it. There are like interesting graph neural networks where you can solve this. But then there's these kind of things, the organic chemists. This is supposed to rotate. Okay. These organic chemists, they come up with all these weird ways to do stereochemistry. This is a molecule that is optically active, but because it has like a counterclockwise rotation in the ring, not because of any particular stereocenter in it. It's a very unusual molecule. And so this one is not capturable by graph neural networks. You can't capture that stereochemistry. So then basically people started working with things called equivariant neural networks. There's other reasons to work with equivariant neural networks, and this is basically putting all the equivariances we can. Atom permutation, bond permutation, translation, rotation, higher order tensor equivariances. And this has led to some confusion literature. There's basically some kind of a nomenclature around this. Body order, which is like how big of a neighborhood you look at. There's the tensor order, which is how big of a message do you pass between these things. I'm just trying to give you a flavor for all this. And then it goes to something called an equivariant message passing neural network. These are, again, more complicated because we have to send messages about atom identities, tensor order to different neighborhoods. And basically, the whole field is a mess right now in what is important for equivariance, because we have all these different inductive biases, and we don't know which matter in what way. And then in the end, if you go look at real learning, like when you actually go to test these things out, we find that the equivariances empirically don't matter that much. So I am showing here the AlphaFold paper, and in the paper they do an ablation, so they delete parts of their neural network to see what mattered. And I'm circled here, this is the basically the equivariant part. So if they remove the equivariance in the AlphaFold paper, they lose, what, 1 or 2 points of accuracy at most. It's a very small change, and it's not that important. And if you look at the amount of effort that goes into just designing the invariant point attention, that's their equivariant layer choice, it's huge. It's a very complicated amount of effort. Okay, so I have this idea, okay, and I have bad handwriting and I can't draw, so I'm going to talk you through it, okay? So here's my idea. Maybe this is other people's idea, but I'll call it my idea for now. So we make things in the lab or on a computer, whatever. Then we have this like shared hallucination that chemical structures are real. You know, nobody, you go take a physical chemist and you push them against the wall and you say, what is a chemical bond? You know, tell me what it is. They'll tell you, I don't know, okay? Chemical bonds are just a shared, it's a hallucination we all agree upon, right? So there's some kind of molecular structure. And then over here we have the measured properties, okay? That is what you go in the lab and you can actually observe. Okay, so what I want to show you is that we actually don't need this thing in the middle, okay? It's really cool, love it, it makes great stickers, but maybe we could try not using molecular structure and see if we can still get predictions, okay? This is the wrong audience, this is the wrong university, the wrong department, but okay. Let's just assume for a minute that we don't need chemical structure, all right. So how do we do this, okay? How do we actually use language to basically predict outcomes? So this is a paper that came out a long time ago. This is from December, okay? And the idea was to take a table of data, okay? So we have tabular data, and this data is like the iris classification. So if you've ever taken any data science class and you want to do some classification, this is the first data set you'll look at. And in this example, basically they took the columns here and they turned them into complete sentences. So instead of having, the sepal length or the sepal width, they have an iris plant with sepal length 5.1 centimeter, sepal width blah, 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 is this kind of an iris. And then they fine-tuned one of these pre-trained models, one of these frontier models, foundational models, base models, pre-trained models, whatever you want to call it. They fine-tuned these and they were able to get good classification performance, okay? Now, if you're a kind of, you're more of a pure computer scientist, you would say, wow, this is ridiculous. You used, a 7 billion parameter model to, do classification with 200 data points or something, right? But on the other hand, if you're more practical, you realize that fine-tuning one of these large language models is like, 2 lines of code, and you don't need to know anything about, SVMs or hyperparameter tuning or anything. You just fine-tune it and it works well. And I'll show you that it does this across many different tasks. Okay, so then we go to chemistry now. So in chemistry, there's this great paper by Kevin Jablonka, very smart EPFL alum. And basically, Kevin took this sentence, the solubility of methanol is blank, okay? So we have turned solubility prediction into an English language test. And he found that if you go across a few different examples, I just took one of the plots from the paper, there's many different examples. Basically, by fine-tuning GPT-3, you could get better performance than all these specialized models, the specialized hyperparameters, inductive biases, things like that. Okay, wow. Okay, but what we want to do is we want to make new molecules, right? So this is cool, but how do we actually use this to make stuff? So we look at something called Bayesian optimization. So Bayesian optimization is a process of choosing which experiment to do next, and it requires 3 ingredients. One of them is uncertainty, one of them is that you can learn as you gather more data, and then one of them is that you can update your models quickly, okay? So this is the recipe. How can we do this with language? I'm not gonna go into too many details, but basically you can sort of turn this question, like the solubility of methanol is X, you can turn it to like a multiple choice question. And then once you turn it to a multiple choice question, you can build this discrete probability distribution. That is, you have a probability of A, B, C, D, E in your multiple choice questions, and then you can build a little probability distribution around that, which gives you uncertainty, and then you can start doing Bayesian optimization with that. So here is now the solubility of 1 bromopropane is minus 1.73 log S. So this is my sentence, and then I can build error bars by reformatting this with my prompts. And then I can have these plots of solubility with uncertainty estimates. And I'm not gonna, just skip over everything, but basically you wanna measure log likelihoods, or you can look at your calibration. So we're trying to make sure that we not just get good accuracy, but we also have good calibrated estimates. And we looked at a few different language models, a few different approaches, like fine-tuning or in-context learning. I won't skip over this. Okay, but so then let's get to this hypothesis, okay? So I've told you that we can do this with the names of molecules. For any of you cheminformaticians out there, you might be thinking, why don't you use smiles? Turns out that that works worse than using the name of the molecule. Interesting. Okay, but so then now what we're going to do is we're going to work in catalysis. Then in catalysis, we're actually going to take the synthesis procedure rather than the name of the catalyst. Okay, so we're making zeolites for heterogeneous catalysis. So I have here a zeolite procedure, and I have my reaction conditions, the synthesis procedure, and then I can predict the yield of my reaction from a paragraph of text. Okay, now before you run and put your catalyst into ChatGPT, just so it's clear, these plots down here after we've gathered like 500 data points or 100 data points. And so it's remarkable that you can do this with 100 data points. Predicting an arbitrary heterogeneous catalysis synthesis procedure's yield is a really hard task, so it's pretty remarkable. But you still need some data, okay? But back to our original idea, if you want to design new molecules or new catalysts, we need to have uncertainty, we need to be able to learn, and then we can do Bayesian optimization. Okay, so the learning part, again, I just want to throw a whole bunch of stuff at you, so I'm going to skip over this, but basically you can look at a few different metrics to make sure that as you gather more data, your accuracy goes up. How do you do this training? You can do it by fine-tuning, or you can do it by in-context learning. Happy to talk more about it, but basically there are ways to update, point by point. And then we get to the most exciting part. So we have a few different models here. This Gaussian process regression is Gaussian process regression. GPR is Gaussian process regression over the latent space using an embedding model, just another metric here. So these are just two different other models that are out there. And basically we can actually go do Bayesian optimization. That is, we make a catalyst, we test it, then we ask the model which catalyst should we try next, then we go and we make the catalyst and we test it, then we go back in and do it over and over again. And this is retrospectively, so we did this a whole bunch of times on a pool of 1,000 or 10,000 catalysts and yields. But then, oh, do I have it? Okay, yeah. Here's the code. Okay, the code is like, it makes no sense. It's crazy. Okay, so like what you do is you tell, then you have the text, and that could be the synthesis procedure or the name of the molecule, then your regression, your scalar, and then you predict to get a prediction out, and then you ask if you want it to tell you what to try next using whatever acquisition function you want. Okay, great. So then we actually went to do this in a real setting. So all of this stuff is, wonderful, and it's great that we can, go back in time and predict things that we already know. But we did this prospectively, so we're making new heterogeneous catalysts for CO2 reduction. Sorry, oxidative coupling. Yes. Sorry, I'm really bad at chemistry, actually. So I have a guy who makes all the catalysts and tests in the lab, and I just tell him what's an important reaction, and he tells me. Okay, so what we did is we made 6 catalysts, and after 6 catalysts, we got within 2 points of the thermodynamic maximum for this reaction. And that's a really remarkable result. One of the problems with this work is that you never know if you're just restating something that was in GPT-4 or GPT-3's training data. So we're repeating this work on a completely new set of catalytic conditions that has never been done in literature so that we can kind of make sure that we have discovered something new. Okay, great. So why LLMs? Okay, so why would LLMs be good at chemistry? So basically, every time we've invented some new method of science or we've done something new in chemistry, we invented new words to reflect what we're doing in the lab. So in a sense, it's not that LLMs are remarkably good at chemistry, it's that language is really good at describing what we do. And it's because it's been this long-term collaborative project of civilization to make sure that language reflects the world around us. So cool, okay? So maybe it works well for a lot of different tasks. Okay, but there's a problem. So it's great that we can make heterogeneous catalysts. It's really cool that we can predict solubility of molecules, but if you ask GPT-4 to count the number of fluorines in my molecule, it'll get it wrong most of the time, which is surprising that it can do these incredible things, and it's really good at interpolating between paragraphs of text, but it can't count very well, it can't do arithmetic. So how do we solve that? Well, the same way that you can solve, you not being good at arithmetic, you can use a calculator. And so that leads to this idea of agents. So now what we're doing is we're asking LLMs to not just predict the outcome from the text, we're asking it to choose which tools to use. And this really only works with GPT-4 right now. It's a very good reasoning agent across a lot of different tasks. People are working on this to make more models, but GPT-4 seems to work quite well. I guess DaVinci 03 is good, but the RLHF seems to somehow affect how well it can work in this tool setting. Okay, so now what we're going to do is we're going to take these transformers, these LLMs, and we're going to give them access to tools and have them do kind of more complicated tasks. Okay. Right, so the first task I'm going to cover is basically answering questions with tools. or grounded answering. Okay, so if you ask GPT-4 this question, I'm not even going to read it out loud. It's a very complicated question. You will get something which is like this. Okay, and it looks, wow, it's like, wow, this is great, GPT-4. There's even a citation at the end of it. There's a problem here is that it's nonsense, right? So the citation is fake, the information is fake, but it looks really good, right? And so this issue is like, it takes like more time to verify this than it does if you just did the research yourself, right? I think I wrote that down. Yeah, I did write that down. Okay. It takes longer to, yeah, okay, that's what I just, okay, great. So then what we can do, okay, is we can actually try to ground these things with extra information. And so now what we're going to do is we're going to ask a question, then give our model some tools, like go look at papers, do a Google Scholar search, pull up the relevant information, and then we can try it again. And then now what we do is, oh, I think I thought I had the same question. Shoot. Okay, it's the same question. Ignore that question at the top. It's the same one as before. And then now we have an answer which is correct, and it has a citation, and I can actually trace the citation back to my document, so I have provenance, so I know that the answer came from this paper. Okay, so cool. No hallucinations. We've grounded the response, and so we know that we're getting answers from real papers. Okay, so we have this whole thing wrapped up into a scientific reasoning agent, we call it, scientific research agent. And basically, you can ask it arbitrary questions, and it will give you back answers with citations. And we don't really have a problem with hallucinations. We have a problem with it saying, I can't find the right paper to answer your question, which is a problem I have a lot. Yeah, like people are into benchmarks. I don't know. There's like one talk that said benchmarks are bad. One talk said benchmarks are important. One talk said like people in the academic community are wasting their lives on low impact work. Anyway, so we did benchmarks. We beat all the other models on benchmarks. So that's great. I don't know, these are important to some people. All right, great. So now that we've done that, now that we can answer arbitrary questions of the scientific literature, let's see what's possible by putting this together with other tools. So now we have a web search, PubChem search, LLM code model, calculator, Python synthesis planner, and this research agent that can answer arbitrary questions. Okay? Then we put all this together and we try to accomplish open-ended tasks. Wow, I can't read that. It says, design a compound with the same mechanism as dasatinib and purchase it. How much time do I have, Philippe? I have 5 more minutes? Oh my God, okay, right. So first step, okay, we're gonna, sorry, okay. We'll just skip a few things. So I want to propose a compound with similar properties to the drug dasatinib. So the first thing it does is it goes to the literature to find out what is dasatinib and what are its properties. Okay, then it finds some other molecules. And then what it wants to do is find the structure of these molecules. 10 more minutes? If I ask again in a few minutes, will I have 15? Yes. The infinite talk. Okay, great. So I need to get some smile strings of these molecules, so it finds another one called imatinib. And then what it tries to do is it tries to make a novel compound. So it takes this compound, which it found in literature that's like dasatinib, and it tries to modify it to make it novel. Then it checks if it's patented to make sure it's really novel. All right, great. So then in the end, it finds this compound, and it says it's novel, it's similar to dasatinib, and then it purchases it from Zinc. So it looks to find out it's purchasable in catalog, and then it sends it to you. Okay, so cool. You know, we just solved drug discovery, right? No, there's a few more steps actually in drug discovery, but that's pretty cool. So then I did this work when I was I did some red teaming for OpenAI on GPT-4. So I did some of this work back then, and then I was really busy, and I was like, oh my God, I need to figure out if this is useful. So I called up Philippe and was like, Philippe, you know chemistry better than anybody else in the world. Can you please help me finish this project to see what I'm doing? And because the reason why I call Philippe is that I don't know, like I said, I don't really know chemistry. So like, I don't know what would be the right tasks, how you would evaluate them. And so Philippe has a great talk. You should see his talk, and he'll talk all about this stuff, but I'm just going to give you the highlights. Basically, we made a tool that has those pieces, and then we connected it to like a robot platform that can make compounds, and then we said things like, make an insect repellent. And then it would look up like, what is insect repellent? What are some examples of insect repellent? Which ones could we make in our robot platform? And then it would make DEET, and then it checked it, you know, the HPLC and what is it, UV-Vis or something, I don't know, yeah, something along those lines. I think FTIR, and then we confirmed that it was DEET. And then another one was find and synthesize a catalyst, but the coolest one was we did actually like make a molecule that has this specific absorption wavelength. So this is to make a chromophore, make it basically a dye to make a nice color. So we said the wavelength we wanted, And then it went out and basically built a machine learning model with some tools. Using the machine learning model, it predicted the wavelength of absorption, and then it chose one that was novel, and then it went and synthesized it, and then indeed it was close to that wavelength. I think Andreas is here, right? Andreas? Yeah, so Andreas, yeah, he did all that work, so you can ask him about it. Great, cool. So how does this work? So it goes through like a few steps here. So we get, here's another example. Synthesize a molecule similar to paracetamol that doesn't contain a methylamide group, then find the price of this molecule, and if it's above $500, plan a synthetic route. Okay, so then it goes and breaks this down into steps with this make an action, make an observation, make a plan basically, then execute it and see what happens. And it's really cool is that this is the same stuff that Bing Chat is working on, but in Bing Chat it's like, I want to take my family on a nice holiday in Berlin. What would be 10 fun things to do? Our budget's like $700, right? So it's cool that we can take that same kind of ideas and apply it to chemistry, because I think chemistry is like planning a family vacation in Berlin, right? So I think it's okay. All right, great. So I won't get into too many details here, but I want to emphasize one thing that's interesting about this is that the evaluations have to be done by experts. Like you can't have GPT-4 evaluate GPT-4. If you look at the plan of something which is all hallucinated versus the plan of something that is real, you have to actually know chemistry and look at it to determine whether it's reasonable or not. So this stuff has to be evaluated by people, and that's a lot of work. And so I hope if there's something that we need to have solved, it's how do we evaluate these agents? Because they're in an environment, right? So it's not like answering multiple choice questions, because they're in an environment where there's like state, basically. As it makes decisions, things change. And then we need to evaluate at the end if it made a good path through it. I mean, this is reinforcement learning 101, but it's a little bit hard in chemistry because we don't really know if it worked until we actually make the molecule, which is, I'm told, is expensive and time consuming. Okay, great. So what about the rest of machine learning? Okay, so we saw some great talks about machine learning and chemistry. They're really cool, but do we have to give all that up and just use transformers for the rest of our lives? No, we can actually make models, machine learning models, emit language. So Gimi here did this research, really cool stuff. I put all of her PhD into one slide here. And basically she made this XAI method where you are predicting solubility. And then if you're predicting solubility, you can then basically identify which parts of the molecule are responsible, and then even get a paragraph of text explaining why a molecule was predicted to have that solubility. And so it says here the presence of the carboxylic acid and a hetero-N basic aromatic group in this molecule are both positively correlated with its aqueous solubility. The carboxylic acid group is especially important as it is highly polar and can form hydrogen bonds with water. Blah, 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 blah. Okay, cool. So like I said, I'm just going to skip over this. There's a nice article about this. But we have methods now where we can have a model that predicts properties. We can have it attach language to those predictions so that we can put it into these agentic workflows where we have machine learning models making predictions and explaining why it made the prediction it did, so that then the agents can react to the predictions. Okay, so basically we have models that can work with language, models that can output language, and we can put it together into agents. Yeah, cool, great. So conclusions. So conclusions. I think we're on the cusp of kind of a revolution in science. Basically, we're at this point now where we can have reasoning agents operating one higher level than we've ever had before. So for example, every time there's a new model that comes out in chemistry or biology or something, we can then put it as a tool in with our agents. And so we're reaching this kind of S-curve, I believe, where we can start making use of all of the papers ever published with our scientific reasoning agent. We can start using all the tools that have ever been made in computational chemistry and putting them together into workflows. And so I think it's a very exciting time to be doing new projects and concentrated projects on what can be done in science with agents. And so that's why I'm at Future House, which is a new nonprofit AI institute in San Francisco. We are basically working on using agents in biology and chemistry to automate science, and we're hiring, so come talk to me if you want a job. Great. See, look, it says joined. Cool. With that, happy to take any questions, and thank you for your attention.
Thanks a lot for the excellent talk. Questions?
Great talk, Andrew. I was curious that you showed in terms of natural language interaction, the model seems to work well for a number of tasks. Was there any task you found that the natural language instruction was not good enough?
Yeah, I mean, sort of a trivial example is that these language models can only predict whole molecule properties, right? So like if you put in like 1 bromopropane and say, like, you know, what is the partial charge on every atom? It's gonna not work. And so, or what are the forces on every atom? So areas where you really need to predict something equivariantly, it's not gonna work very well. As far as in other tasks, you know, there are some problems with, okay, how do I say this? These things are really good interpolators. Okay, so like if you have like 10 examples, it's really good at interpolating around these things. If you go to like very low shot, or you go to something very generalizable, right? Like you involve, you know, some class of molecules here, and then you switch to maybe, you know, something with bromine in it or something. It doesn't really generalize well, and that's because it's not really grounded on physical principles. It's grounded in language. In other areas it doesn't work well is if you have made-up tasks. So there are like kind of adversarial examples, like, you know, say if this molecule has 2 fluorines or not. That it doesn't do very well and things like that. So you can come up with examples that are pretty, you know, to break it. And it is difficult because, you know, it's hard to know ahead of time if it's going to work well. But I think if you're at the point where you have like 25, 30 examples, it's a really effective method to use in this setting.
Hi, thank you for your talk. I have actually 2 questions. The first one is about, I mean, we all know that we can express molecules in very different aspects, so smiles or like graphs or like, I mean, fingerprints and so on. And I was wondering if like multimodality was helping there, and if you were actually using it, and if it was also like scalable and stuff. So that's my first question. And the second question is about like origin and already behind.
What was the second question?
Origin, graph neural networks already behind, or like, do you still believe they can?
So the first question, multimodal. No, we didn't do any multimodal. We've looked at multimodal a couple times, and yeah, it just hasn't made sense because, like, you know, if you have a molecule, the graph is a restatement of it, and if you go add the coordinates, if you have a deterministic method of generating the coordinates, they're also a restatement of the graph, which is a restatement of the smiles. So in most of the stuff that I've seen, multimodal hasn't helped, except if it's like extra, you know, really like an extra channel of information. And your second question, do we have to leave them all behind? No, I don't think so. I think that especially in, you know, so in those examples, if you have 500 data points, the best model is not a pre-trained LLM that you fine-tune. The best models, if you have 500 data points, is, you know, a carefully built neural network. If you get, you know, 2,000, then definitely a graph neural network, especially a pre-trained graph neural network, they are better. So I think these are really good models for when you have low amount of data, yeah, like you're not going to do AlphaFold with fine-tuned GPT 3.5. But if you're in a lot of times in chemistry, we're in kind of a low data regime, and that's where these things are really excellent.
Andre Villarreal, thank you very much. This is extremely inspiring to think that you know, some kind of a symbolic representation of a scientific world could be resolved in this other way. I'm curious as to the experience that you have with different size and different types of LLMs. I mean, including open source ones relative to GPT-4.
Yeah. So I would say GPT-4 is just on another level when it comes to reasoning and complex prompts. Like, I'll give you a specific example. One of our prompts is like, here are 10 citations of papers that might be relevant to answer a question. Identify which of the 10 citations could be relevant by writing down the key for the citation. They'll have like little keys attached to them. Llama or what else do we try? Falcon. They just can't handle a prompt that complicated. Even GPT 3.5 can't handle that, but GPT 4 and Claude 2 actually both can handle that kind of a prompt. And then when it comes to using tools, basically many models just can't follow that in a zero-shot setting. Certainly with fine-tuning, they can get to it and they can achieve it, but it can be difficult if you're like swapping tools in and out, changing how you want the tools to work, to use these open source models. I think we're going to get there. I talked to some people from Hugging Face about like methods to kind of rapidly iterate on this. So I think we can get there with open source models, but right now it's just nothing compares to GPT-4 on most reasoning kind of tasks.
Can I have a bit of a follow-up? Because there's no other question, I guess. I'm curious as to the window size of a context that you can use, because I know you would talk about fine-tuning, we talk about embeddings, but yeah. Can we somehow expect that a much bigger size window relative to your experience may be actually enabler to this kind of results, or not the right path relative to fine-tuning?
That's a great question. So I would say in my experience, longer context didn't really change much. So we did some work on like feeding in lots of papers or feeding in very long context. And it didn't really work that well. And the reason why is that a lot of the power from these things is like this autoregressive nature is like, summarize the 10 key points of this paper. From these 10 key points, identify what was the evidence supporting them. From these 10 things and evidence supporting them, write down the 3 major results, right? And just like these what really is powerful is this autoregressive nature of these models where it can sort of show its work and do this chain of thought. Adding longer context windows doesn't help that much. However, we have found some interesting use case with longer context with parsing. So sometimes you have some big document, and like this traditional approach now is that you have a really good parser and then you chunk it and you put it into a vector database. Now, if you have something like a PDF and like the PDF has 2 columns, and when you parse it, the columns don't line up or something like that, you can just throw them into something like Claude 2, and Claude 2 can read this very long jumbled thing and still pull out relevant information to answer questions. So I have seen some good uses there, but I would say longer context is not really a path towards better performance on most tasks, except for it makes your life easier because you don't have to think as carefully about designing your input prompts or your context.